Hello, this is MAT 221. This is Mrs. Johnson. This is Calculus 1. We're in section 4.6, which talks about optimization and modeling. This is in applications to the derivative. Just like with related rates, these problems are some of the most difficult that we'll study in calculus because they are word problems. They are real-world application problems. And they're hard and difficult because we have to come up with the actual equations to study and move on as we use the calculus. So we're going to use the methods that we did in sections 4.1, 4.2, 4.3, 4.4, to all look at those things that we studied in this unit to come together and talk about optimization, which is similar to section 4.3 when we talk about finding the extreme values or the best or the worst or the highest or the lowest of something. And we also have to model these equations, so we have to come up with equations ourselves. So I'm going to go through this PowerPoint, but then I'm also going to go through a worksheet with you that I have on modeling and optimization, similar to what I did with related rates. So let's start with this PowerPoint. So first of all, when we talk about optimization problems, just like with related rates problems, there's definitely a procedural value thing that we need to go through, these procedures. The first thing we need to do is understand the given problem and try to identify the information you need to solve the problem. Just like with related rates in section 4.1 of this unit, we'll see that we'll usually find that somewhere in the problem it's asking us to find the highest, the biggest, the greatest, the smallest, the least. So that's going to be our hint to know that we're talking about optimization problems. So we need to usually understand the problem and identify what information we need to solve for the problem. And just like with related rates, we try to draw a picture of the situation and label the parts that are important. Introduce all our variables which make sense to us in the problem, and then state what we need to maximize or minimize. Remember, this is an optimal problem, so it usually is asking you to find the highest or the lowest or the biggest or the smallest or the greatest or the least of something, or the maximum or minimum of a function. Next, we have to try to write a function given the information that we're talking about. If necessary, we need to get this function in terms of only two variables, which we also had to do with related rates sometimes by looking at other information that was given to us in the problem, or we have to go back and rely on our history in mathematics to either our geometry or our algebra or our trigonometric skills to help us write these functions and simplify them if necessary. The next thing we have to do is also make sure we find a domain of the function that makes sense and determine what values will make sense in the problem. Because these are real-world problems, sometimes we'll get an equation that models the situation quite well. However, we know in real life certain values won't make sense. For instance, if we're talking about a cubic on the interval from -infinity to infinity as our model, but we're talking about maximizing the profit of a company, we wouldn't necessarily look at negative values for the input, in that our time or our amount of items that we sell is never going to be a negative value. So we might get an extreme there on the actual function, but it won't make sense in the actual problem. And hopefully you'll see this as we go through and do some examples of optimization problems. And then lastly, we need to identify the critical points and the endpoints to solve the problem. Determine if the critical point is a min or max by either using the first or second derivative test, and then decide if your result makes sense to state your answer. I know it seems pretty simple, but just like with related rates, we know that these can get quite difficult. So let's look at a classic problem to start. This one says we have 40 feet of fence to enclose a rectangular garden along the side of a barn. And we don't need the fence along the barn. We're going to connect the fence to the barn. So we don't need fence along the barn. We just need the 40 feet of fence to enclose the other 3 sides that don't include the side along the barn. And the question is asking us, what's the maximum area that you can enclose? Now, again, it looks so innocent, this problem, but it is not. It's actually very difficult as we go through. But let's try to see if we can set this up. So if this is our barn, and here's our barn here, and here's our rectangular fence that we're putting alongside the barn. So we have 3 sides of fencing. Excuse me. If I called the width of the enclosed rectangular area, this rectangular garden, if I call that X, then I know this is also X because that would be the width of the rectangle. Now, if I have 40 feet of fencing, I know that if I have this is X amount and this is an X amount and I have 40 feet of fence, then I know that the length is going to be the 40 feet of fence I have minus the 2 width lengths, which are both equal to X. So the length of my garden can be represented by L, or can be represented by the 40 feet of fence I had minus the 2 X's that I already used for the width of this fence. Now it asked me to maximize the area, so I put in an equation for area of a rectangle, which is equal to length times width. So in this case, my width was equal to X, and my length was equal to 40 minus 2X. Now, once I have an equation that is talking about the maximum area, in other words, this is what I want to maximize, once I have a formula or an equation that has something here of what I want to optimize, my procedure for using the first or second derivative test comes into play. So I'm going to take this equation and now find its maximum values. So I distribute the X, so I get my area is equal to this quadratic. Now, how do I find maximums or minimums using the first or second derivative test? I take the first derivative. I set the first derivative equal to 0 to find the critical points. In this case, by solving for X, I get only 1 critical point. Next, I have to determine this. There must be a local maximum here since the endpoints are going to be minimums, right? But we should also test by using the second derivative test here, or the first derivative test, to determine that this is actually a maximum value. So this means that the width of this would actually be 10 feet, and the length must be 40 minus 2 times 10, which would be 40 minus 20, which would be 20 feet. So then we have to go back here and actually ask, what is the maximum area? So they're asking me, what is the maximum area that I can enclose? Well, if I know that the maximum width will occur when X equals 10, and the maximum length will occur when X equals 10, then this must be my length and width of my garden. Therefore, my maximum area that I can enclose would be 200 square feet. Now on this PowerPoint, I actually don't do it here, but we really should actually always check to make sure that this value here is a maximum value. We can easily do it by actually taking the second derivative here. If you took the second derivative of this function is equal to -4, which tells me the function is always concave down because the second derivative is always -4. And if the second derivative is always -4, that means that the original curve must always be concave down. So any point that I had that was a critical point must have been a maximum in a concave down area, which we also know this from the parabola, right? This parabola is going to be a concave down parabola, so the only critical point I would find would be at a maximum. All right, I'm going to do another example here on the PowerPoint, and then we'll get to the worksheet that will actually help us too. Okay, what dimensions for a 1-cylinder, 1-liter cylindrical can what dimensions for a 1-liter cylindrical can will use the least amount of material? Again, let me go through a couple things that we know here. Remember with related rates, in our problem, we always had a rate somewhere. We had a rate of change. We could see it from its units. Notice there's no units like that here. And they're also asking me for the least amount of material. Least amount, smallest amount, minimum value. So this is an optimization problem because of what they're asking me for. But it's not really that clear what they're actually asking me for. The least amount of material, what does that mean? It means I want to know what's the least amount of the surface area of this can. Now we're going to have to go to Google or to our textbook to look up the surface area for a cylinder if you don't know it, and that would be given to you. But we can minimize the material by minimizing the surface area. Now the surface area of a can is actually given by this formula, which is 2 pi r squared, which is actually the two circles that are the top and bottom, and then 2 pi r h, which is the lateral area around the outside of this can. Now if you notice, we need some other equation that will relate r and h because we have too many variables here. We have a, and we have r, and we have h. So when we have too many variables, we sometimes try to get rid of one. Now they gave me this right here, that this 1-liter can is equal to 1,000 centimeters cubed, which means that's its actual volume. So then I go to Google and I go, well, what's the volume of a cylinder? The volume of a cylinder is pi r squared h. And I know that the volume is 1,000. So I could substitute 1,000 into the volume equation. And then I could solve that equation for either r or h. And I'm going to solve it for h here because I only have one h in the equation but a bunch of r's. So I took this equation of volume and I'm going to reduce this equation, which is the one I want to optimize. Remember, I want to minimize the amount of material in the area or surface area. So this is the equation that I want to minimize. I take this equation that I just found using the given information that they gave me, and I substitute it into this area equation. And when I do that, I can simplify this equation a little bit and get my area equation is equal to 2 pi r squared minus 2,000 over r, or I could write this as 2 pi r squared plus 2,000 r to the negative 1. So I don't have to use the quotient rule. All right, now I have an equation. If you notice, I have this equation for surface area in terms of just two variables, the area and the radius. Now I take the derivative with respect to r. I set that derivative equal to 0. I solve for r, and I get this value. Now, I should determine whether or not this is a least amount, which means I want it to be the smallest amount of material here. So what I do now is I go back and I solve and I put this value in for my r value, so I can now solve for h because they're asking me what are the dimensions, which is the radius and the height of the can. So I had one dimension, which is my radius, and now I had to go back up into this equation for the height of the can to get my equation for, or my value for, the height of the can. All right, I know that those examples are quite difficult to start with. I am going to go step by step through some more examples in your PowerPoint, in your from your worksheet folder from section 4.6. There's also another PowerPoint that's quite old that goes through some examples that has worked out examples in it also for optimization in the Blackboard folder. Have a good day.